So here an represents the nth term of a GP, and we have two sum that's having a value of alpha and beta. We need to show that the common ratio is given by alpha over beta. So let's begin. Now, since we have a geometric progression, we'll need to specify the first term and the common ratio. So let the first term be and the common ratio be represented by the letter r in lowercase. Now, we'll start with the first summation. We have summation going from n equals to 1 to 100. Then we have a to n. So this will be equals to alpha. Now, expanding the summation, our first term will be a times a to n means a2. Then the second term will be a 2 times 2, so that's a4. Then we have the third term, which is a6. And this goes on to the 100th term, so that will be a2 times 100, that's 200. So this sum is equals to alpha. Now we know that since this is a geometric progression, our second term a2 that can be represented as a times r. Then our fourth term will be a times r cubed. The sixth term will be a times r raised to the power of 5. And going to the last term, the 200th term will be a times r raised to the power 199. So this value is equals to alpha. So here this is clearly a geometric progression with the first term. So this is our first term having a value of ar. Then we have the common ratio, which is given by the second term divided by the first term. So that will be r squared. So using the formula for the sum, then this sum, the summation of this entire series is going to be equals to, we have a, the first time, a times r whole multiplied to r squared raised to the power of n. The total number of terms here, since this goes from 1 to 100, so that means there are 100 terms here. Minus 1 divided by common ratio minus 1, so common ratio to r squared, so r squared minus 1, that's equals to alpha. So let's label this as equation number 1. So let's work with the second summation. So here we have the sum going from n equals to 1 to 100, and then we have a 2n minus 1, so this is equals to beta. So expanding the summation, we're going to have a times a of 2 times 1 minus 1 plus a 2 times 2 minus 1 plus a 2 times 3 minus 1. All we're doing is replacing the value of n with n equals to 1, 2, 3 respectively. So the final term will be a 2 times 100 minus 1, which will be equals to beta. So that means our first term is a1, followed by the second term, which is a3. Then the third term is a5. It goes all the way up to the last term, which is a199. So this is equals to beta. Our first term a1, that's going to be a, followed by the third term, which is ar squared. Then we have a fifth term, which is ar raised to the power of 4, going all the way up to the last term, which is ar raised to the power of 199 minus 1, that's 198. So that's the value of beta. So this is also a geometric series with the first term being a and the common ratio r squared. So we have a, the first term multiplied to r squared, which is a common ratio, raised to the power of 100 minus 1 divided by the common ratio minus 1. So this value is equals to beta. So let this be equation number 2. Now what we'll do, we'll divide equation number 1 with equation number 2, which is equals to alpha over beta. So here we have r squared minus 1 cancelling out, r raised to the power of 200 minus 1 also cancelling out, a and a cancelling out, and thus leaves us a final value r equals to alpha over beta. So hence we have successfully showed that the common ratio is given by alpha over beta.